let's say we built a cannon and we decided to fire a cannonball directly up in the air with some initial velocity v. We'll just call that we'll call the initial velocity v. Okay. Well, we know that eventually it's going to go up to some height, and then it's going to come back down. But what if we wanted to fire it so fast, that it never comes back down? How do we know how hard what initial velocity we need to give it for that to happen? Okay, so we can actually figure this out by using conservation of energy. Just setting E initial is equal to E final. So our initial energy is just 1/2 mass times the velocity of the cannonball squared minus the mass of the cannonball, mass of the Earth, times g, all over the radius of the Earth squared. I'm sorry, all over the radius of the Earth. And then, and we have to include this potential energy because remember, the cannon is sitting on on the Earth, and it's actually this, it's this gravitational energy we're trying to escape from. So we need to make sure that we include the term that we have on the Earth. Okay, our final energy is going to be 1/2 mass times our final velocity squared plus our potential energy at infinity. So in other words, remember, our potential energy at infinity in the gravitational field is our definition of zero potential energy. And also notice that essentially what we're really saying is we just want it to be able to get to infinity. So it can get all the way to infinity and then have no velocity there. So we'll also set this term equal to 0. So in other words, we're saying that the total energy of our system, if our final energy is 0, that also means that our initial energy is 0. So if we solve this, we see that 1/2 mv squared is equal to m times the mass of the Earth, g, over the radius of the Earth. We can cancel out the masses. And so we see that if we give it some initial velocity equal to the square root of 2 times the mass of the Earth, g, over the radius of the Earth, or the square root of 2 times the radius of the Earth times the acceleration due to gravity, this is what we call our escape velocity. So this is the speed that we need to give something if we're not going to give it any later acceleration, if it doesn't have a rocket or anything. This is the velocity we need to give it in order to escape the gravitational pull of the Earth. Okay, but then that brings up an interesting question. What if what if our velocity is bigger than our escape velocity? So in this case, again, our initial energy is 1/2 mass times velocity squared minus the mass times the mass of the Earth, g, over the radius of the Earth. But now we're going to have some zero final velocity. So this is going to be 1/2 m v final squared. Once again, we can cancel out all the masses. We can multiply by 2. So we see that v final squared is equal to v squared minus meg over 2 meg over re. So in other words, the final velocity is equal to the square root of v minus v escape, because this term we see is just the exact same thing as v escape squared. So in other words, if our velocity is equal to v escape, then our final velocity is equal to 0. But if we give it some initial velocity larger than the escape velocity, then that's telling us that we're going to have, a non-zero final velocity. So if we say that we want something to escape the Earth and have some final velocity when it's very far away, this is the velocity that we're talking about.